will be giving talk on the topic melting and substrate-induced phase transitions in two-dimensional liquid crystalline systems of soft ellipses.
Good afternoon, all. So let me thank the organizers for giving me the opportunity. So today what I'm going to talk about is the melting of a liquid crystalline system in 2 dimensions. And I'll be, if time permits, I'll be talking about 2 cases. One is the 2-dimensional system is free, and another case is the 2-dimensional system is under the influence of a underlying substrate. So in liquid crystalline systems, there are these different phases. At high temperature, you have isotropic, and then if you reduce the temperature, you go from isotropic to nematic to smectic to crystal. Okay, so in terms of the order that you see in 2-dimensional systems, the work starts from 1930s, go up to 1960s, and then in the 1970s, you get the defect-mediated melting theory by these 3 people, and there is one more, David Nelson, who was here last year. Okay, so defect-mediated melting means that in 2-dimensional systems, at finite temperatures, there is no perfect positional order. And what happens is, at very low temperature, you might have a crystal, but that crystal is not perfect. So there are always these defects. These are called dislocations. Dislocations are a pair of 2 particles which have other than 6 nearest neighbors. So if it is perfectly hexagonal system, then every particle will have 6 nearest neighbors. But in this case, at the center, you see the green and the red ones. They always come in pair at low temperature, and that's when you call it crystals. And that type of pair of defects is called dislocation pair. If you increase the temperature, then this pair breaks down. You individually get dislocations. So dislocation is a pair of green and red particles, meaning particles having 5 nearest neighbor and 6 nearest neighbors. Then if you increase the temperature further, then these dislocation dissociates, and you get disclinations. And disclination means individual at random positions, the particles having other than 6 nearest neighbors. Okay, so that's the scenario in the KT-NHY theory. So in my case, so what I was interested in is that in the liquid crystal, the particles are not spherical, they are elongated. So in that case, there are 2 types of order introduces in the system. One is the positional order, which is that I described, and another is the orientational order. So my question was, how does that orientational order plays a role into the melting of the system? So here, each of the particles are represented by some interaction, and that interaction is called Gay-Burney, which is a derivative of the Lennard-Jones potential. Lennard-Jones is spherically symmetric, and Gay-Burney is asymmetric in such a way that it gives you the it's set up in such a way that ultimately it gives you the interaction represents a ellipsoidal kind of particles. These are point particles, but the interaction is ellipsoidal in its nature. Okay, and then, so what I'm going to look at, so I would run the simulations at various different temperatures and densities and look for some order. So first order to look for to determine the positional order is called the radial distribution functions. And if the radial distribution function has nice peaks, then we say solid-like. If it doesn't, then we'll decide. If the profile of that radial distribution function goes like algebraic decay, solid, exponential decay, liquid, and then to determine whether it's somewhere in between, and that's the hexatic phase, then we have to look for another order parameter called the bond orientational correlations. So these, I'll show some plots. And the other one for the liquid crystalline system specifically, we have orientation correlation functions. So each at different places, how the molecules are oriented. So if they are oriented along the same direction, you have orientational order. So that's through that function. So here is the snapshot of the different systems at different temperature and densities. So on the top, temperature 2.2. On the right bottom corner, you have 1.5, and the green means positional order. Each of the particle have 6 nearest neighbors. Other than green is that particular particle doesn't have 6 nearest neighbors. So at low temperature, almost it's green, so most likely crystal. However, you see these defect lines, and yesterday, in one talk, Professor Debabrata, he showed something very similar to this. And I'm still not sure why these things come, so I had some discussion, but it's not, I'm also not clear why these only 2 defect lines spanning the whole system appears always. But however that may be, so these are my results. We go increasing the temperature, you go from crystalline to ultimately isotropic liquid case, and there is this somewhere in between state, and this state is going to be my hexatic state. Okay, so these are the close-ups of the systems. So here you can see these defect lines have this, colored particles. They are in a combination of 5, 6, 5, 5, 7, 5, 7, 5, 7 nearest neighbor particles. And they form a defect line. And in this case, on the lower corner, you see these pairs appear randomly in other places. So that's where the appearance of the hexatic phase. And then they dissociate, and you see everywhere individually or connected defects. So it's isotropic liquid case. Then we are start talking about liquid crystals. So we'll look into the direction of each of the molecules. So on the top, each of the molecules are more or less directed. There is temperature, so a little bit of fluctuation. And as you increase the temperature, they randomize completely. So isotropic liquid and the solid. Okay, now I also look at the fraction. How many of the particles have six nearest neighbors? How many of them have 4, 5, 6, 9, and so on? But so what you see here is that as you increase the temperature for a given system, as you increase the temperature, the green one, which is the number of, or the fraction of particles having 6 nearest neighbor, decreases. So that indicates somewhere the melting is happening in between. And these ranges gives me, I just wanted to show where the hexatic phase lies and solid and isotropic liquid phase lies. Okay, so these are the correlation functions. Look at the right top curve. Here you see for some temperatures, I have the horizontal line and then somewhere in between inclined line. So log scale on the left-hand side. So the inclined line represents hexatic phase, and the horizontal line represents the solid case. So in this way, I form this kind of a phase diagram where I show where is my hexatic, where is my solid, where is my nematic in the plane of temperature and the density. I'll end here. Thank you very much.
Thank you, sir. Let's have some questions from the audience.
So what was the aspect ratio that you used?
3:1.
3:1.
Yeah.
Any reason for that choice?
So 3:1 is like the lower bound. If you are below that, then the liquid crystalline behavior and so there was a long back study in 1996 around by Frankel, and he showed 3 is like the lowest one. And as I increase the aspect ratio, the simulation slows down. So I took the easier pathway. Other than that,
but
nothing.
To see nematic at aspect ratio 3, you might need to go to very high densities.
Indeed, yes.
But here I can see like at very low densities, you're showing a nematic phase. So
This is it's a relative term, low, high.
No, no, I mean, do you have a finite S in a nematic phase? Do you have, like,
Finite S?
I mean, the nematic order parameter? So how
So
do you
at
define?
these densities,
Mhm.
at high temperature, nematic phases do
It's
appear.
there.
Yes, yes,
Okay.
yes.
Okay. Okay, sure.
Okay, thank you. So exotic phase represents, it doesn't have positional order, it has bond orientational order. Meaning each of the particle are having environment mostly 6 yes or no. Okay, so this is the G of R, which is which would tell me whether they have positional order. Okay, so one system may not have positional order, but it may have bond orientational order, meaning it may have a lot of most of the particle having 6 nearest neighbors. And to identify that, you look at this G6, which I showed. This is the expression for the G6 here. And when you plot this G6, it looks like this. So on the top, you see that black curve, which is more or less horizontal. So if it is a hexatic phase, then this curve would not be horizontal, meaning long range orientational order is not there. It would be logarithmically or algebraically decaying nature. So it would be like this. And if it is horizontal, it's solid. If it is like this, then it is hexatic. If it goes down like that, it's a liquid. If you want, I can show you this expression in more detail, why that happens. Okay?
Thank you, sir.
So what is the nature of the transition? Are they continuous or discontinuous?
That I don't know. My PhD student working, maybe in the next couple of months, I'll tell you.
Okay. Thank you very much, sir, once again.
Thank you very much.
Okay.